So the first thing, every rotation can be defined as the composition of reflections in two intersecting lines. The triangle XYZ is reflected in line M, producing X prime, Y prime, Z prime, which is then reflected on line N to obtain the double prime. And so what you can actually think of for rotation is two reflections. So they took this first line here, and they took their pre-image and they reflected it across that line. And you can see that it is mirrored across that line. Then they have this intersecting line, and they reflected it again. And so the way that you define your rotations is the degree of those two intersecting lines. So if I were to describe this rotation, I would say this is a 60-degree rotation counterclockwise. All right, counterclockwise. Because these are the two lines that created that reflection. And from point to point, when you start at one and go to the other, that is the reflection. And so if I were to look at this point on the line and the angle that is created when it got all the way over here, that's going to be 60 degrees. And so while you can't measure this, you measure the lines that are created from that intersecting line. And so you can do it with construction. If you look, the definition is a transformation defined by its center. The angle of rotation is so that if you were to map one point onto the other, what is the angle that's created? And so if you look at how they do it, they actually take the point and they create an angle based on what it wants you to do. So they wanted to rotate this 85 degrees about C. And so they've actually drawn the line, created an 85-degree angle. After they create the angle, they measure from C to M prime, and that's where they know the new M is going to be. And they do that for every single point in the quadrilateral. They would draw a line from N to C, and then they would create an 85-degree angle there. And for every single point, they would create an 85-degree angle. And that's how you would do it with construction. You can also figure out by construction what the angle is. They create a perpendicular bisector between the two and then figure out the angle between those as well. But we're actually going to do it on the coordinate plane. And so if you look at the coordinate plane here, we're going to start with this first one. So a couple things. All the rotations that I give you are going to be counterclockwise. All right? Counterclockwise. Because I'm going to give you a set of rules for these. And so the way that you're rotating them obviously matters. Counterclockwise goes the opposite direction of a clock, right? So we're going around this way. This first one we're starting out with is a 90-degree angle. And so we have a 90-degree angle here. This black image here is my pre-image. This red is my image after it's been rotated. And so you can see that 90 degrees in the coordinate plane takes it from one to the other coordinate, which makes sense, right? These are all 90 degrees each, all right? And so if we were to draw from Q down to the origin and to Q prime, we would have a 90-degree angle. If we were to draw from R down to the origin and up to R prime, we would have a 90-degree angle. And same thing for S. S down to the origin over to S prime would be a 90-degree angle. That's what it means by a 90-degree rotation. All right. And you'll see that we're going to use our coordinates just like we have for everything else. Remember in our reflections, when we reflected across the x-axis, my y changed from positive to negative. So we're going to use some of those same shortcuts with these. You'll notice that when we rotated 90 degrees, what happens with my x's and y's? Well, they not only switch places, but it negates the y value once it's changed, right? Flipped over. So it goes from 1, 2 to negative 2, 1, from 4, 2 to negative 2, 4, and from 3, 4 to negative 4, 3. They switch places, and my y value, my original y value, negated. All right? The next one is 180 degrees. So now we've gone across twice, right? 90, 90 is 180. And so it basically flips all the way across here. Now what you'll notice is my x and y's didn't change places this time, but they all negated. Every one of them negated, which makes sense if you think about this logically. My x's and y's are both positive here. My x's and y's are both negative there. And so they don't change places for 180, but they do negate. And then the last type of rotation that we're going to have is a 270, which basically walks it all the way around from the first to the to the second, from the second to the third, and the third all the way to the fourth. And here you'll notice they again switched places, but that my original y's were negative. My original y's negated here. And so there is a shortcut. Page 475, you're going to need to know these shortcuts. 90 degrees. It goes from xy to negative yx. From xy to negative yx. So you negate your y and then switch them. Negate your y and then switch them for 90 degrees. For 180 degrees, you go from xy to negative x, negative y. They don't switch places, but they all negate. Everything negates. Whatever it was, it's the opposite for 180 degrees. And then at 270, you go from xy, you negate your x this time, and they switch places. Negate your x, and they switch places. So it goes from xy to y negative x. I want to forewarn you, you're going to have a quiz on all of these, including your reflections. And so you need to make note cards or something, flashcards, Quizlet, whatever you want to make, so that you remember these switches. Because what's going to happen is you're going to try to combine your reflections and your rotations, because we have shortcuts for them, okay? And so you're going to make sure that you know which is which for these, all right? So these are your shortcuts for counterclockwise rotations around the origin. For 90, you go from xy to negative yx. For 180, xy to negative x, negative y. And 270, xy to y, negative x. All right? So let's do an example. Look at example 3 in your book, page 476. Find the coordinates of the image of the vertices of F, G, H after a 270-degree rotation about the origin, and then graph it. All right, so this is what your questions are going to look like. I'm actually going to request that you give me the vertices of your pre-image, the vertices of your image after the rotation, and then I'm also going to want you to graph it. So it's going to be a 3-part question when I give something like this. And so what you want to do is you want to give me the F, G, and H vertices. And so if I look at F, I'm at 1, 2. If I look at G, I'm at 0, 3. And if I look at H, I am at negative 3, negative 2. All right. Negative 3, negative 2. Those are my original. Those are my pre-image. They want me to translate it with a 270-degree rotation. So all of these are going to change. And if you look at your shortcut here, 270 negates the x's and then switches them, right? Negates the x's and then switches them. So my new coordinates for F prime here, my y is not going to negate, but it is going to be in the x place. And then my x is going to negate and be in the y place. My x is going to negate and then be in the y. For G prime, again, my 3, which is in y, is going to become my x. I cannot negate 0, so it's just going to be 0. And then my H prime, my negative 2 is going to become my x value, and then that negative 3 is going to negate, meaning it's become positive 3, and it's going to be my y value. And so that's the first step, finding your vertices and finding your new vertices, okay? And then you need to graph your new one. Now on any type of homework or quizzes or tests, you can graph it on the same exact graph, right? But we're going to graph it on a new one. So it's going to look like this. F is going to be at 2, negative 1. So I'm going to go to 2, negative 1 and graph my F prime. G is going to be at 3, 0. And then H prime is going to be at negative 2, positive 3. And then once you have those, you want to just connect them. So connect them to make sure that you have the triangle that you were looking for. And you've rotated it. Now, if this were on the same graph, they would actually be on top of each other, which is fine. In any translation, they could actually end up partially on top of each other. I will say there's one other type of rotation that you may see that's not in this book is a 360. Where do you think a 360 is going to end up? Same spot, right? So those are really easy rotations because it all maps onto itself. Okay, it maps onto itself. So check your work. A rotation should keep this congruent. So it should not skew your size or your shape at all. So when you do these transformations, this particular one, this one will not change the size or the shape. It should just change the orientation, okay? So if you start to connect those dots and it looks like a different figure, you need to go back and check what you did and make sure that you did it all correctly because it should look like the same exact triangle, just rotated around the origin. It's just going around. Now these actually give kind of a complete rotation is what is happening here with like a Ferris wheel type thing. And what they want to know is they want to know how far they've traveled in degrees. And so it says the giant wheel at Cedar Point Amusement Park in Ohio contains 36 passenger cars. How many degrees must it rotate before the next passenger car is loaded? And so when they give you how many points of rotation you have, which we're going to talk about rotational symmetry a little bit, but they have 36 buckets. The entire circle is how much of a rotation for the entire circle? 360. So for something like this, you would just take the 360 and you would divide it by how many you have. So this is just going to be 10 degrees that it has to actually travel. It says if it takes 20 seconds to unload and load a car, how long does it take for a newly loaded car to rotate to the top of the wheel? To the top of the wheel. For half that circle should be 180. And how many degrees is each bucket? 10, right? So we know that we have 10 degrees per car. All right, so it takes 18 cars being loaded for someone to get from the bottom all the way to the top. And then they told us how much it is per car. How much is it per car to load it? How many seconds per car? 20 seconds. All right. So we get 360 seconds. That's a weird way to say it. I'd probably say that in minutes. How would I convert seconds to minutes? How many seconds are in a minute? So I'm going to divide by 60. So it takes about 6 minutes just to get loaded, for half of that thing to get loaded. All right. So sometimes they're going to give you how many points there are, and they want to know how far it has traveled in that rotation. And you're just taking the full 360 divided by the number of points you have. All right. Let's look at just basics of isometries, page 481. Page 481. So the first thing I want to talk about is an isometry is a specific type of transformation, and all the ones that we have done so far have been isometries. It is a transformation that preserves the distance. They basically mean that preserves the shape. You're not changing the distance between the points when you move it. So we did reflections. Reflections kept them congruent. That was an isometry. We did translations where all you did was slide it around the graph. That was an isometry. And now we've done rotations. And all three of those are isometries. They're a specific type of transformation that preserves the distance. It doesn't skew the size or the distance between the points, all right? It does not skew it. And so they give you reflection, translation, rotation, identity transformation, and composition of isometries. Identity just means that it puts it on itself like a 360 would. Composition of isometries we've already done with rotations. It was two different reflections that happened there to get a rotation. So these three are the ones that we're going to be looking at. Reflection, translation, rotation. These are just a more specific type of the ones that we did. Identity is just like a 360. It just reflects or rotates on itself. Composition, rotations are actually a type of composition. All right. And so they give you the pictures here. You can see that when we were to rotate this around, if we were to measure the distance from A to B, it would be the same. Same if you reflected it and same if you slid it. So the distance between those points doesn't change. The angle or even a polygon doesn't change. It is still congruent to where you started for isometries. All right. The next thing we're going to look at in this section is called a glide reflection. A glide reflection. So let's look at the definition. It's a composition of a translation followed by our reflection in a line parallel to the translation vector. All right. And so they give this example here. Find the image of the triangle RST after a glide reflection followed by the translation vector 5, 0 and a reflection in the line y equals 0. All right. And so they've given us this picture here. Triangle TRS. The first thing they want us to do is slide it 5, 0. Now 5, 0 just moves it which direction? 5 moves it left or right? Positive 5 moves it left or right? It moves it right. And the 0 means it did not go up or down. All right, it did not go up or down. The line y equals 0, that's actually a special line. What is the line y equals 0? We have a name for that. What is the line y equals 0?
The y-axis, or the x-axis?
Yeah, it's the x-axis. Y equals 0 is just the x-axis. So all they're saying is slide it over and then reflect it across the x-axis. All right, that is a glide reflection. All right, you are gliding it, meaning you're translating it, and then you are reflecting it across the line that's parallel to how you slid it. And since we did not slide it up or down, it's going to be parallel to the x-axis, that slide is. And so it looks like this. The glide reflection, it slid it over 5, 0, and then it reflected across this x-axis. So the first, and you literally do it in 2 steps. You do the translation, slide it across the graph, and then you take that and you reflect it. So you have to remember both of those rules. This just adds 5 to all your x's, right? Didn't do anything with the y's. This one, all it did is change your y from positive to negative. Remember, when you reflect across the x-axis, you negate your y. So this is what this looks like. We went from xy to x plus 5 negative y. That's what that did. You added 5 to all your x's and you negated all your y's. And that took care of both of these in one description. Both of these in one description. Does everybody see how they did that? So they just did all of these movements with one description algebraically. All right. Look at this next example. They want us to look at this and tell what happened to it. All right. So they go from ABC. This is all of my original right here. And they want us to go to DEF. All right. If you look at this particular one, this is just a regular translation. All they did was move it over and up, over and up. And so if you look at the answer there, they went over 4. So if I were to describe this using a rule, the rules look like this. I'm going to tell exactly what's happening to my x's and y's. They went over 4 and up 2. Over 4 and up 2. So you can look at this next one is a rotation. It's just like your shortcuts. So they just said it did something like that. And so you can actually do these descriptions with just parentheses instead of all the words out. Instead of saying rotating around this axis or rotating around 270, you can give the shortcut. Or instead of the slide, you can just say what's happening to your x values there. Right? And so every isometry can be expressed as a composition of at most 3 reflections. At most 3 reflections. Because you're going to get to the point where it then maps on top of itself. And so this is one of your theorems. One more example and then we're done. Graph the polygon with the given vertices, then complete the glide reflection defined by the vector and the line of reflection, and then state the new rule. So here's what we're going to do. We are going to take this triangle and graph it. So in your graph paper, you're going to graph that triangle. Then you're going to do the glide reflection. You're going to slide it the way it tells you to, and then reflect it across the y-axis, and then you're going to write a new rule in one statement to describe what happened here. All right, and you can write the new rule first and just do the new image. You don't have to do 2 of them, or you can do 2 of them and see what the new rule should be, whichever way you want to do it. But your final image needs to show both of these, this slide and this reflection. So check your work. Your new rule looks like this. Because of you flipping across the y-axis, your x would have negated. And then the 0, 4 would actually add 4 to every one of your y values. That's your new rule, negative xy plus 4. So then that would give you your new coordinates here. That would give you your q double prime. The reason there's a double prime there is because you've done 2 transformations. 2 transformations, all right? Now, when you're given something like this, you're only required, if you start with this guy, to do your finished product. But if you want to look at it to make sure you did the rule correctly, you can move it up first, the 0, 4, and then you can reflect it across the y, and you can see what those are, all right? So that's why I drew that yellow just kind of dashed there. This is your first movement, your slide, and this is your second movement, your reflection. But if you go straight to the new rule and your new set of coordinates, then you can just graph your new sets of coordinates, all right? And you can kind of see if that looks like you did it correctly just by based on visually what it looks like.